This is Algebra 2 at Trig 3A.2a. We're going to be graphing simple rational functions. So a rational function has the form y equals p over x divided by q over x. The p over x and the q over x are just polynomials. So this would not be considered a simple one. This would be like y equals x plus 2 over x minus 7. A little bit more complicated with those. We'll do those in the future. But that is what a rational equation is. Essentially, it's having an x in the denominator. The inverse variation function that's what we use for inverse variation. This is a rational function. This is a more simpler rational function that we're going to work with today. The parent function for a simple rational function has a parent function of 1 over x. So y equals 1 over x is as basic as you can get for this rational function. Okay, is a rational function which consists of two, I'm going to take that back. Yes, it is a rational function, but we're already talking about that. Sorry about that. We're going to call it a hyperbola. That's what we call these shapes. Hyperbola. Which consists of two symmetrical halves called branches. The domain and the range are all non-zero real numbers. What does that mean? All non-zero real numbers. So we're going to say all real numbers, that's our little abbreviation for all real numbers. Typically it's a comma. All real numbers except when we talk about a vertical number, x number, we're going to say x equals 0. Or we're going to say all real numbers except y equals 0 for the range. Let's talk about what this vertical asymptote is. Why can the graph not touch where x equals 0? It can't touch that because 1 over x, you can't make that fraction become a 0. There is no number. Let's take our calculator real quick. There's no number we can divide by 1 to make 0. We can get close to 0. Okay, what does that mean? This is times 10 to the negative 5th power. So it's 0.00001. You take that decimal point and you move over 1, 2, 3, 4, 5. You move over 5 spots. So it's 0.00001. Scientific notation. So this is the way the graphing calculator represents scientific notation. So you can get close to it, but you can never equal 0. Okay? So there's no value for x that is going to make the graph equal 0 for the horizontal asymptote. Now, what about the vertical asymptote? I implied that that was the vertical asymptote. But the vertical asymptote is, why can't we use 0? Why can't I plug 0 in? What would happen if I did 1 divided by 0? What number is that? That is undefined. That gives us this error because we're dividing by 0. You can't divide by 0. That's like taking $1 and giving it to no one. Someone's got to get it. You can't divide $1 by 0. You can divide $1 by 2, 50 cents a piece. Okay? But you can't divide $1 by 0. So that's what an asymptote is. It is a line that the graph approaches but never reaches. That's an asymptote. We have a horizontal asymptote. The graph is approaching but can never reach. And we have a vertical asymptote. The graph can get closer to it, but it can never reach. Okay, any function of the form y equals a over x, where a is not 0, has the same asymptote, the same domain, the same range as our parent function. All that's going to change is a vertical stretch. And we'll talk about that. All right, when we graph this out, we're going to graph y equals 4 over x. We're going to graph that. We're not going to use our graphing calculator. So you should not use a graphing calculator for this and poof, have an answer, but without any work. So we know that this graph, y equals 4 over x, is in the format of a over x, which is just like the parent function. So it's going to have the same asymptote as we're expecting. You can't reach, you can't use a 0 in your calculation. So when we try to use 0, what is the answer? There is no answer. 4 divided by 0 is undefined. So we don't have an answer. We don't have a y spot because the graph does not touch the vertical asymptote. Now we have to pick 4 spots to the left of that vertical asymptote. Now let's use our brains a little bit. Let's use smart numbers that are going to work well with 4. What are some numbers that work well with 4? What goes into 4? Let's start with -1 works well with 4. -2 works well with 4. 3, yeah, we could probably do it, but 4 works better with 4. So at -1, when x is -1, 4 divided by -1 is -4. So I can put my dot there. 4 divided by -2 is -2. No, it's not. It's -1. Sorry. And 4 divided by -4 is -1. Okay, correct. This is -1, but I plotted this in the correct spot the first time. Psyched myself out. 1, 2, 3, 4. Sorry about that. Little confusion. We need to pick values to the right of the vertical asymptote. We want to pick values that work well with 4. So 1 works well, 2 works well, and 4 works well. So 1 goes into 4 4 times, 2 goes into 4 2 times, and 4 goes into 4 1 time. So when x is 1, we're up at 4. When x is 2, we're up at 2. And when x is 4, we're up at 1. And we can connect those points. Notice that the graph is never going to touch or pass the y-axis. And it's never going to touch or pass the x-axis. It'll always get closer and closer. It'll go on forever. You can do 1 over 1,000. You can do 1 over, or in this case it's 4, but 4 over 1,000 or 4 over 1,000,000. You can go out as far as you want to go out, and it's still never going to give you a negative answer, or never give you 0. The vertical asymptote. We have that labeled. It's kind of hard to see here, but it's dashed, and we label our graph, x equals 0. We have a horizontal asymptote that the graph is approaching. Would like you to come through here. That is y equals 0. It's called the x-axis. What's our domain going to be? What x values does the graph cross? What x values are you allowed to plug into this equation? Those are your domain. You can plug in negative numbers, you can plug in positive numbers, you can plug in fractions. Is there any restriction for what x can't be?
So it can't be 0.
So all real numbers except x equals 0.
Good stuff, Chuck. Way to go, bud.
And what about the range? We see that the range is down here at -4, it's down here at -2, it's down here at -1. And every value in between. It's even up here at 1 and at 2 and at 4 and every value in between. But it doesn't touch the point 1 1, but for y is 1, it happens right there. And when x is 1, it happens right there. So the graph exists when x is 1. The graph exists when y is 1. But it will never touch when y is 0. That's the range. So all real numbers, you can touch any y value except y equals 0. So what is our comparison? How does this graph compare to y equals 1 over x? Here is your graph of 1 over x. 1 over x is touching that 1 1 spot. But when you have the 4, that gives us a multiple of 4, so a vertical stretch. So we're going to move this spot up 4 times as much. Not 4 steps, that would take you to 5. But 1 times 4 is 4, and that's why we're at 4. This is a half. So a half times 4 is 2. So that's why we're at 2. Minorly interesting. It's just a vertical stretch. By a factor of 4. These, whenever we're multiplying, this is just 4 times 1 over x. 4 times, so the 4 would multiply the 1, so we have 4 over x. We're multiplying the parent function by 4, so that is stretching it vertically by a factor of 4.
So if you're dividing or sharing anything, or no?
Okay, let's flip the page. All right, here with this one, take a look at this equation. At first it might seem scary because it has a fraction in it. But then it should start to look familiar because it has an h and a k. And what does h and k do?
This stuff might be up top.
The h and the k, the h gives it a horizontal translation and the k gives it a vertical translation. So it is going to move the graph just like it did with the vertex in the past. This doesn't have a vertex, but it is going to translate it like it has in the past with our vertices. All right, we're going to draw the asymptotes. We know that the asymptotes are where x is going to be the h value and y is going to be the k value. We're going to plot 3 points to the right of the vertical asymptote and to the left of the vertical asymptote. That's when we use the table. We're going to draw the 2 branches of the hyperbola so that they pass through the plotted points and approach the asymptote. We could put an S on that because there are 2 asymptotes. There's a vertical asymptote and a horizontal asymptote. So we're doing the same graph, but then we're going to translate it. So we're going to take a look at this. We're not going to make our table based off of this whole equation. That would take a lot of different calculations. That would make the job a little bit more difficult. We're not just plugging in points and chugging through. We're going to use the graph y equals negative 3 over x. We'll call that our parent function. It might be better to call it 3 over x, but I'll save you the time to do the reflection. So we'll just do that in our first calculation. We're going to make a table that works with this, and then we'll translate it 1 to the right and 2 up. Remember, it's the opposite of the h value, just like it's been all year, because it's x minus h. So if we're going to graph this one, we know that we're going to have a vertical asymptote at 0. We're going to pick 3 numbers to the left of that that's going to work well with 3. Well, negative 1 works well with 3. Negative 3 works well with 3. And I guess we could say negative 6. You could use 2 if you want. That's pretty easy to plot a point at 3 over 2. But these are going to work pretty well as well. So when we put a negative 1, negative 3 divided by negative 1, what would that give us? Negative 3 divided by negative 1. Negative 3 divided by negative 3. And negative 3 divided by negative 6. Some people make a mistake and they say 2. But 3 is on top of the 6. So the 2 has to be in the denominator. So we can plot these out. We're going 1 to the left and 3 up. We're going 3 to the left and 1 up. We're going 6 to the left and a half up. So it still approaches our vertical asymptote, and it still approaches our horizontal asymptote. So now we're picking 3 values to the right of the vertical asymptote. We talked about 1s, 3s, and 6s work well. So negative 3 over 1 is negative 3. Negative 3 divided by 3 is negative 1. And negative 3 divided by 6 is negative a half. So when x is 1, we're at negative 3. When x is 3, we're at negative 1. And when x is 6, we're at negative a half. Now, I did not draw my asymptotes in here just to give us limited information on a graph. We'll put the final asymptotes in. So what we're going to do now is to draw in our asymptotes. We know that our h value is going to be 1. X minus h, using our format of x minus h. So the h value is a positive 1. So the graph is moving to the right 1. So we can put our vertical asymptote in there, and that is x equals 1. We know that the k value is going to be 2. So that is y equals 2. Then we can move. We got 2 choices. We could move our points 1 to the right and 2 up. So 1 to the right and 2 up. 1 to the right and 2 up. 1 to the right and 2 up. And we could draw in our new branch. The other suggestion is to take these asymptotes, take our table, and do our calculation from there. So using this as our new origin, you could go 1 to the right and 3 down. So that's 1 to the right, 1, 2, 3 down is right there. That should be the same as 1 to the right and 2 up. You could go 3 to the right and 1 down, which is going to be the same thing as 1 to the right and 2 up. So whichever format that you like best, 1 over and 2 up. So we have a vertical asymptote. Where is the vertical asymptote? X equals 1. Where's the horizontal asymptote? What is our domain? What are the x values that are appropriate to plug into this? Anything that doesn't make the denominator 0. And what's that going to be? The asymptote tells you that you can't use that number. You can't use 1. So you can use any number, all real numbers, except the h value. X equals 1. And the range answers that you're going to get, you can get any number you want except y equals 2, the k value. So we've translated our graph 1 right and 2 up. We had a reflection over the x-axis. That's what the negative did. That's why this branch is in the lower right-hand corner, and that the left branch is in the upper left-hand corner. And we also had a vertical stretch of 3. So that gives us all our transformation information. So what did we do? We noticed what our h and the k were. We recognized our a value was -3, so we made our table based off of that. We plotted these points, we plotted the asymptotes, and we translated those points using our h and the k. Okay, last story problem. The time t in seconds that it takes for sound to travel 1 kilometer can be modeled by this crazy equation, where T is the air temperature. How long does it take for sound to travel 5 kilometers when the air temperature is 35? So this is a calculation for 1 kilometer. We want to know about 5 kilometers. So what we're going to do is figure our answer out for 35 degrees. Then we're going to multiply that answer by 5. If this is a formula that sound travels when the air temperature is 35, it travels 1 kilometer at 35 degrees. .6 times 35 degrees Celsius plus 331. This would be a calculator type question. We're showing our work. Divided by, now you need to be careful here. You've got to use parentheses if you want this all to be in the denominator together. 0.6 times 35 plus 331 should give us 2.84. 2.84, these should be seconds. That's to go 1 kilometer. This would be per kilometer. So we're going to say 5 times 2.84. So we're going to take that answer and multiply it by 5, and we get 14.20 seconds. That's per 5 kilometers. Now, one way to have thought about that is to have come up here and multiplied our numerator by 5 right away. So it was 5,000, and we would have gotten that 14 right off the bat. Either way you think about it. But that's the math.